Alright guys, welcome to the video on sections 3.1 and 3.2. Again, before you start watching this video, I encourage you to print off the PowerPoint that I'm going to be using. This is in the same email that you got the link for the video. Also, I encourage you not to sit down and watch this in one sitting. It's going to be somewhat long, so I don't want you to get burned out halfway through. So do this in stints. I encourage you to probably do it in, say, 30-minute chunks. As you're going through here, please write down any questions that you have, especially on the PowerPoint. You can bring that to class. You can email it to me, and we'll be happy to talk about, excuse me, anything that you want to talk about in class. I just want to make sure we, don't lose an entire day with me not being in class next Thursday. So, as I told you previously, the class is going to kind of operate where we talk about a particular type of function and different things that go with it, and then we'll move on to the next type. So the first unit was kind of introducing functions. Chapter 2, which is what you just had your test on, introduced linear functions and some different things with it, some different applications, and now we're going to move on to quadratics. Now your next exam, and I'm referring to the one that will be due the Tuesday after you come back from spring break, although you can complete it during spring break. The one that you will do online is going to focus on actually 3 different types of functions. So we're talking about quadratics in chapter 3. And then chapter 4 is actually a chapter about a variety of other nonlinear functions. So chapter 2 is about linear, chapter 3 and 4 are about nonlinear functions. And we're just going to kind of pick 2 sections out of chapter 4 because those are the 2 common types of functions, most common types of functions that you'll see if you go on to a different class, the quadratics plus the things in chapter 4. So chapter 3 is nothing but quadratics. Just know that chapter 4 is also nonlinear functions, but it has something to do with something other than quadratics. So anyways, this is going to be, excuse me, sections 3.1 and 3.2. on quadratics. So this first section, we're going to look at basically just like, let's define what a quadratic is, some different things that we need to graph it, and some applications and such for that. There's a couple of things on this slide that I have in the PowerPoint, but I don't want you to worry about, although I felt, hey, it's in here, let me go ahead and use it. But anytime you see something that talks about completing the square, you can ignore it if you want. We're not going to particularly talk about completing the square. We're not going to use it. So if you see completing the square somewhere, don't worry about it. There are ways around it. For us, it's not that big of a topic, so I don't want to spend a significant amount of time talking about completing the square if it's not something that's a necessity for us. Additionally, you'll notice that there's something called quadratic regression. So in chapter 2, I sent you a video on linear regression, and regression is a statistical topic. This is not a statistics class, so I don't want to harp too much on regression. Although, for those of you that have had statistics, you did linear regression, and there are other types of regression, for example, quadratic regression. So if you see those things pop up anywhere, you can ignore them if you want in terms of class assignments and the tests and things like that, but they're obviously there if you want to peek at it. Okay, so let's talk about quadratics. So first off, chapter 2 was about a linear function. So remember, we defined it as mx plus b or ax plus b. I have the mx plus b here. But notice the general form of that, and notice the functions that I have below are not linear. They do not fit that mold, specifically because they have this x squared term in them. And because they have the x squared term in them, they are by definition not linear. Again, keep those general forms in mind. Now, let's define what a quadratic is and what's the general form for it. A quadratic function needs to look like this. So just like we have a mold for linear functions, we have one for quadratics. A, B, and C can be anything as long as it's a real number. Again, think back to chapter 1, but it can be anything that's a real number. The only restriction on this is that A is not allowed to be 0, meaning that you have to have an x squared term in the function for it to qualify as a quadratic. Now notice that there are no restrictions on B and C. B and C can be any real number. It's just that A can't be 0. So there's our general form for a quadratic. So Note that if you have a b or a c that's 0, you won't necessarily see those terms, but there is a requirement to have the x squared term in order for it to be a quadratic. So you'll notice that all of the ones that you'll look at today and then the rest of chapter 3 will have the x squared term. The graph of a quadratic, some of you may know, is called a parabola. And generally we have this terminology of saying that a parabola opens up or opens down. It is a lot of times described as a U-shape, so you might imagine where someone came up with that terminology as opening up or opening down. So if it looks like a U, then we call it it opens upward. And then sometimes it may open downward, which just means kind of take the U and make it upside down. The way that you can notice, or at least have some insight into the graph based on the symbolic representation, so again, this is the symbolic representation here. The way you may have some insight into knowing whether or not the graph opens up or down is by what the value of a is. If a, again, that's the coefficient that's attached to the x squared term, if it's positive, then you know that your parabola is going to open up, and if it's negative, the parabola will open down. Note that b and c, again, I'm referring to this, a, b, and c here. Note that b and c are not mentioned here. It does not matter the values of b and c. It's only a that will determine whether or not that thing opens up or opens down. So when you're graphing a quadratic, there are some important things to note. First off, you kind of want to know going into it whether it opens up or down. So right, you should have some sort of expectation of that going into it. The other thing that you'll want to take note of first is where what we call the vertex is. Now the vertex is the highest point on the parabola or the lowest point. If the parabola opens upward, then we would have a lowest point, and that would be the vertex. If the parabola opens downward, then we would have a highest point, which would also be the vertex. So if you look at, say, a graph of a quadratic, and this is a quadratic, note the form over here, then notice in this case the vertex is this lowest point right here. And I'll show you how to find that in just a second. But again, important things to note. Does it open up or does it open down? And the first thing you're going to kind of want to take note of is where's the vertex at? Okay, so here are some graphs that you can see there with different functions. Again, note the values of a. Again, a is the thing that's attached to the x squared, not necessarily the first number that you see. So be careful with that because it may be written in a different order like this example here. Notice that it's not written as ax squared plus bx plus c. It's actually written as c plus ax squared, and in this case the a is negative 1 specifically, so you note that the parabola is going to do this downward opening, and therefore the vertex is what we call the highest point. The other thing you want to take note of when you are graphing a quadratic is where the axis of symmetry is. Now the great thing about the axis of symmetry for a quadratic is that it has to go through the vertex. And it is a vertical line, so note that here, it is a vertical line, so it means it goes up and down, and it will go through the vertex. So if you look back at, say, this example, and this one here, the axis of symmetry is the y-axis. So what we mean by the axis of symmetry is essentially that it's a line of symmetry, meaning that what happens on the left-hand side, a mirror image of that happens on the other side. So in this case, the y-axis is the axis of symmetry, and in this case, this dashed vertical line is the axis of symmetry. Now, this is not actually part of the graph. It's not part of the function. It's just an imaginary line that we know exists when you're graphing quadratics. So it's not something that you would necessarily graph. It's just important to note that it's there. So that's the axis of symmetry. So first off, know if the parabola opens up or opens down, know where the vertex is, and then also take note of the axis of symmetry. So here are a variety of different parabolas. You can note the differences in how the parabola is graphed based on its form, which, as you might imagine, if you change things in the symbolic representation, meaning the equation, it's going to change what the parabola looks like. Now you'll note that also all of these have the vertex at the origin. So every one of the graphs that you're looking at has the vertex at the origin, and you may start to notice some things about the functions that are here, particularly the symbolic representations, and why the vertex is at the origin. Yeah. based on their forms, but that's not important at this moment. Just take note. You may start noticing some things there. Okay, so again, this is just kind of what I was saying earlier. When you start looking at quadratics, you want to note a few things. Does it open up or down? Where's the vertex at? And where's the axis of symmetry? So in this case, you see a parabola, and it opens downward. So since it opens downward, that means that the a is negative, right? The coefficient of the x squared term has to be negative because it's opening down. Also, you can note the vertex here, in this case, which would be a maximum point or a highest point, is at negative 2, 5, which is this point here. I can't plot it, but you can see the ordered pair here, and obviously it's the highest point of the vertex. Because the vertex is at negative 2, 5, that means that your axis of symmetry goes through the vertex. Since it's a vertical line, it has to be of the form x equals something, so it has to be x equals negative 2 in this case. Now, notice that it's not graphed or highlighted here, but do note that if you look at this line here that I'm tracing over, that it acts as a mirror image, meaning that you could kind of fold the coordinate plane at this line, right? This would be your fold line, and you would get mirror images on each side, right? The images or the other sides of the fold would touch each other, right? It would be a mirror image. I don't want you to necessarily get too caught up in increasing and decreasing because we didn't get into that really in chapter 2. But if you take note, increasing means that the slope between any 2 points that you're picking is positive, and decreasing means the slope between any 2 points that you pick is negative. So if you pick any 2 points where the x is less than negative 2, so that's to the left-hand side of the axis of symmetry, if you pick any 2 x's to the left of this line, you'll get a slope that's positive. Now you got to have 2 points, right, because you're talking about a slope. And if you pick any 2 points to the right of this, you'll find 2 points that have a slope that are negative. But both points have to be either to the left or to the right for that to happen. Do start taking note of the domain and range here. For this one, the domain is always going to be all real numbers, or negative infinity to infinity. Quadratics, the domain is always going to be that, unless for some reason there's some sort of restriction. But for general purposes, the domain is all real numbers. The range is going to be limited, right? Because these quadratics are going to have either maximum or minimum points. So you won't have an all real numbers as your range. In this case, it's all the numbers that are less than 5, right? We don't use any y as any number as a y coordinate bigger than 5. They're all below 5, or including 5. Okay, vertex form. There are 2 different ways to look at a quadratic. We've already looked at what we call the standard form of the quadratic. That's this one here. If we look at this, we call that the standard form, right, where it's that ax squared plus bx plus c. There's also another form called the vertex form. As you might imagine, the vertex form is going to tell us where the vertex is. Now you may be going like, oh, I hope that I always get the quadratic in the vertex form. Well, it depends on what you're trying to do. So in general, right, it is easy to find the vertex if the quadratic is in vertex form, but it's harder to do other things, or at least it would require more work to do some other things. So don't get too hyped up about the vertex form. Now, in the vertex form, you'll notice that it's drastically different. Notice again, there's a restriction on a. It can't be 0. But in this case, you get the vertex for free. It tells you that if it's in this form, that the vertex is at h and the hk, where h is the x coordinate of the vertex and k is the y coordinate of the vertex. Do to take note of the form here, this being negative and this being positive, if it looks exactly like this, then your vertex is hk. So be careful with that. Because, let me give you an example. If you have, let me fill in some numbers here. Right, in this case, your vertex would be 4, 5. But in this case, right, your vertex is, I need this to work, is negative 4, 5. So again, it's got to fit this mold here in order for you just to pull the vertex out. Now you may be wondering, like, why in the world is that the case? Again, we kind of ran into this issue when we had circles, and it's because of how you would have to write this in order for it to fit that form. So if I want to have a negative here, or a subtraction, which is what this form looks like, then for me to compensate for that, I would also have to make this negative 4. Oops, too many negatives there. There we go. And now we've got, nope, that's not right. There we go. And now we've got it written in this form exactly, so now we can pull out the x and the y coordinates. So just be careful with that, in terms of the signs. But if it's in that form, you get to just pull the vertex out. Again, take note that A is the same A, right, that we looked at in the symbolic representation. So it's the same A. Again, if it's positive, it opens up. If it's negative, it opens down. Again, take note that if I put a negative here, this does not change the vertex. So my vertex or my vertices are still the same that I have here. So in some cases, the quadratic would be in vertex form, and in some cases, it would not be. So you may be going, well, what do I do if the quadratic is not in this vertex form, and I still want to find the vertex? So what if it's in standard form? For example, like this, right? Oops, don't want to do that. If it's in standard form, the ax squared plus bx plus c, then to find the vertex, you can use this little formula. Again, I'm not going to go into it right now in terms of where these are coming from, but to find the x coordinate of the vertex, you would take the opposite of b over 2a. So again, the a, b's, and c's are coming from the standard form. And then don't get caught up too much in this y coordinate. The y coordinate looks ugly, but again, keep in mind how you find outputs. To find the output, you just plug in the input into the function. So if we know that the x coordinate is the opposite of b over 2a, then to find the y coordinate, just plug that number into the function, and then whatever the output is the y coordinate. So that's what this f of opposite of b over 2a is. It looks ugly, but again, it's nothing new. We take a number, we plug it in, we get the output. And that's all that notation is. So here's an example of going between the two forms of the quadratic. So you'll notice that in this case I have the quadratic in standard form. So if you want to find the vertex, right, opposite of b over 2a, and you find that the x coordinate is -2, and then again to find the y coordinate you plug it in, so that's what's happening here, so you can follow along with the algebra there. And so the vertex is at -2, -5. And so that's the case for this quadratic. And then if we want to use that to put it in vertex form, then keep in mind, all we have to do is to take the values that we have and plug it into that form. Again, note that 3 is still a, so that's why this is still 3 here. And then again, your x coordinate is -2 and x minus -2. Again, the minus is kind of part of this form or formula. So you got to plug in the -2 and then plus k, which in our case is -5, plus negative is the same thing as just subtraction. So that's kind of two birds with one stone, taking this function and converting it to the vertex form, but you're also seeing how to find the vertex when it's in that standard form. When you're graphing quadratics, again, you need a couple of things. First, you're going to need the vertex. The axis of symmetry is important, but you don't necessarily need it. I mean, it's right there wherever the vertex is. Know whether or not the parabola opens up or opens down, and be able to find at least one other point on the graph. But again, that's nothing new. Finding points for functions is just inputs and outputs. So plug something in, you get something out. That's an ordered pair. That's what we did with functions. No matter what the function is, that's always the case. So if we have this quadratic here, again, note that it is a quadratic. It fits our mold of ax squared plus bx plus c. And we can pull out the b and the a in order to find the vertex. So that's what's happening here. Now, it's a little ugly with that fraction in there, but make sure you can get that with the calculator. And you'll find the x-coordinate's -1. So to find the y-coordinate, you'll just take -1 and plug it in to the function, right, to get the output. Take the input, plug it in, get the output. So the vertex is at -1 and 5/2. That means that the axis of symmetry goes through the vertex. Again, it's a vertical line, so it's going to have to be x equals something. And then we know that the parabola opens downward because the a is negative. So that'd be the things that we need in order to graph the quadratic. Now, I told you also need at least one other point on the line, not on the line, on the graph. So in this case, you need the vertex, which we just found is -1 5/2, and then you need another point. Now, the reason I only say you need one point is because of the axis of symmetry. Now, obviously, you can graph it like we did here, where we did 3 points on each side. Or you can actually just find this point, and because of the axis of symmetry, there's got to be a corresponding point on the other side at the same y value. If you don't like doing that, then you can do a couple of inputs and outputs. So here are a few examples of this. Now again, to find this ordered pair, all I did was pick a x value, -4, and I plugged -4 into this function. And again, you got to plug it in here where it says x squared. You got to plug it in here where it says x, and simplify that, and you should get -2. Where did I get -4 from? Well, I just picked it. Remember, the domain of quadratics is all real numbers, so it doesn't matter what x value you pick. It's defined for all x values that exist, all real numbers at least. Okay, so applications and models for quadratics. The reason that quadratics come up a lot is because any kind of projectile or anything that's falling or kicked or thrown or shot follows the path of a quadratic. If you let x be time and y be the height, then any kind of object in the air is going to follow the path of a quadratic. So that's why it comes up obviously a lot in physics and a variety of other applications. I'm not going to go into every single one of these things. I don't want to overwhelm you with the video, but you have access to each one of these, and you can kind of see how these applications are used. Again, I think this may be something we might be better served for in class, but I'm going to leave this up to you. If you have questions about this, fire away. If you want to bring it to class, fire away. But I think the detail in the work here is pretty good. But if you have questions about where anything came from, please let me know, and I'll be happy to walk you through this. Obviously, the vertex is going to be a pretty big deal in any application because it's the highest point or the lowest point, depending on depending on which way your quadratic opens up. Okay, so what I would encourage you to do at this point is to take a break. That is all of section 3.1. And then, so I encourage you to pause and kind of come back and with a kind of fresh mind and kind of collect your thoughts with any kind of questions that you have right now on section 3.1. Walk away and then come back in a little bit and we'll do section 3.2. I'm trying to pause it. There we go. Hi guys, so hopefully you've taken a break and are ready to talk about 3.2, or at least hear about. So in the first section we kind of talked about what quadratics were, what the form was, what the graph would look like, different aspects of how the symbolic representation impacts the graph. And so now we will talk about one of the things that we're going to want to do with quadratics, and that's to be able to solve them, or specifically to solve quadratic equations. And as you might imagine, a quadratic equation is an equation where the equation contains a quadratic expression. So just like we solved linear equations, remember I showed you how to do it mostly with your calculator, we can solve quadratic equations. And there are a variety of ways to solve quadratic equations by hand. So those are the different ways of doing that. Again, you'll notice that completing the square is one of those options. And again, I'm not going to ask you or require you to do that. Again, it is a useful method, but again, you got to know how to complete the square to do that. And again, if you want to know that, by all means, let me know, and I'll be happy to show you. But for the purposes of our class, it'll be one of those things that's not that important for us. But factoring, the square root property, and the quadratic formula will be important. Those will be the three ways you'll be expected to solve. And when I say that, I don't mean that I'll say, here is a quadratic equation, solve it using factoring or whatever, whichever one of those methods. It'll be up to you to which method you choose. You might start to notice that some methods for solving quadratic equations are better suited for a particular type of quadratic. But again, most of the methods can be used, well, let me say this. The quadratic formula can be used in any situation. Factoring can be used in a lot of situations. And the square root property only can be used really in a couple of situations. Completing the square is like the quadratic formula in that you can use it on any quadratic, but you got to be able to complete the square, and then from there it's some algebra, which basically boils down to using the square root property to solve the quadratic. So again, not going to ask you to do that. The discriminant is going to be something that comes straight out of the quadratic formula, and then there's some applications again for solving quadratics, solving quadratic equations. So, what is a quadratic equation, and how is that different than a quadratic function? Well, a quadratic equation is not really concerned with inputs and outputs. It's comparing two things, specifically in our case, a quadratic to something. So, in here you see that it's a quadratic equal to 0. Now, the reason that this is set up in terms of setting it equal to 0 is because many of the methods, specifically the factoring and the quadratic formula, will necessitate you setting the quadratic equation equal to 0, so essentially getting it in this form. But it doesn't have to be in this form to make sense of what's going on, specifically thinking about how we solved linear equations using graphing and using the calculator. But in any case, you'll notice that in a lot of the examples that you'll see, or if you hit help me solve this or what have you, it's going to ask you, or it's going to get you to put the quadratic equal to 0 to start off with. And again, the reason for that I'll explain further in just a second. But what I don't want you to lose here is that all we're looking for is when a quadratic, in this case, sets up equal to 0, or specifically, and we'll write this just a slightly different way, if you let f of x, no, don't capitalize that. If you let f of x equal your function, right? And let's say your function was originally set equal to 0. So let's say this was your quadratic equation, and you're curious, when does the left side equal 0? Well, if you let the left side just be f of x, then the question that you're essentially asking is, where is f of x equal to 0? That's the same as the original question. So this part here, 3 times x plus 4 squared plus 5 equals 0, is the same as f of x equal to 0. Where does that happen? Maybe it doesn't require a question mark. So if you keep in mind what we've thought about inputs and outputs, f of x is the output. So it's basically saying, where does the function 3 times x plus 4 squared plus 5, or whatever quadratic, where is the function equal to 0? Where does it have y values that are 0? Where are points that have y coordinates that are 0? Now again, it's not always going to start off with 0. But I have a slide that will hopefully help you understand the difference and what we end up with our solution in just a second. But all you're basically saying is let's call that a function, right? Because we can, and then we'll figure out where is that function equal to 0. So that's going to help us when we kind of try to visualize this in graphing. So if again, and this sets up the slide on the picture on the next slide is thinking about this equation here. Where is it equal to 0? Again, it won't always be 0, but that's kind of like the standard form, and you'll want to get it to 0 in many cases. So notice that at the top in these boxes, all of your quadratics are set equal to 0. And if that's the case, and you just let your function be the x squared plus 1 in this case, so the x squared plus 4x, negative x squared plus 4x minus 4 here, and then whatever this one is. And notice they just wrote it as y. They didn't write it as f of x. They just wrote it as y. But if you let it be that, then you're basically just saying, where does the function have a y coordinate that's 0? Well, if you have a y coordinate that's 0, that means that you're on the x-axis, which means you're an x-intercept. So that's why you're seeing this box C that says it's referring to x-intercepts. So if I show you a picture of that, maybe that will help. So let me turn these off. So if I slide my tool here, notice that all of the, notice that all the y coordinates are 0. No matter where I put my cursor on this line, the y coordinate is 0, which is f of x. which means you have an x-intercept. You're crossing the x-axis. So that's why that picture is referencing x-intercepts. So a lot of times people will say the solutions to a quadratic equation are x-intercepts, because they essentially are, if you have it set equal to 0, which again, like I said, you will do, or you'll be asked to do, or it'll set up for you to do that, setting it equal to 0 in just a second. So these were already set equal to 0, so we can just reference them as x-intercepts. So I hope that makes sense. And you have these, and if not, please let me know. But there's these different cases, right? You could have a quadratic that never touches the x-axis, which means it has no x-intercepts, which means it has no solutions to this equation set equal to 0. It could touch the x-axis once, where the vertex is the x-intercept, and that's the case in the middle. Or you may have the case where you touch the x-intercept, the quadratic crosses the x-axis twice, which is this case. And again, keep in mind the quadratic could be opening up or opening down in any of these situations. So these are the three things that could happen, and we're going to hear that again. 0 solutions, 1 solution, or 2 solutions in a minute when we talk about the discriminant. So again, be expecting either none, 1, or 2 solutions when you're doing this. And we have these 4 basic methods for solving quadratics. And again, I'm not going to show you the completing the square, but just know it is another alternative method for doing so. So we'll talk about the first 3. If you're going to factor to solve a quadratic, then you need to, again, I don't know if this is going to influence necessarily how you solve a quadratic equation, but it's worth noting because we kind of need this property. We need something called the zero product rule, or the zero product property. And basically what that says is if we just look at this piece here, it says A times B equals 0. Well, if you multiply 2 things together, what has to happen for you to get a result of 0? And the only way that you can get 0 when you multiply 2 things together is that at least one of them is 0. Now, so that means A is 0, or B is 0, or both A and B are 0, because 0 times 0 is 0. So, but at least one of them has to be. Doesn't mean that they both are, but one of them has to be at least 0. So that's all that's basically saying. So that's setting us up for what we're about to do. So if we look at this quadratic here, 12t squared equals t plus 1. And again, it is a quadratic because we have the variable squared. And we're trying to find solutions to this equation. Notice that in the steps down here, the first thing that happened is that we set the equation equal to 0. And again, we're doing that to set us up to solve by factoring using the zero product rule, or the zero product property that was on the last slide. Now, I don't know how much you remember from factoring, but once you factor, and if you're having trouble in these 2 steps here, how we factored, we can talk about that. And maybe that's something we'll talk about in class on Tuesday. But if you're having trouble with this, we'll talk about that. But let's assume right now you got it factored. If you factor it, then notice that I have something multiplied by something else, and somehow I'm getting 0. And what that basically means is that either this is 0 or this is 0. Now, again, remember t can be any real number, right? Remember the domain of quadratics is any real number. So at some point, t may make this 0, the 3t minus 1, and then at some point t may make this 0. So we just want to figure out when that happens. So all we do to do that is to set each one of these equal to 0, because that's what we want to find out. We want to figure out when, for what value of t do we get 0 from 3t minus 1, and for what value of t do we get 0 from 4t plus 1, which is what you're seeing down here. So again, for this one, you'd add 1 and divide by 3, you get 1/3. Here, you'd subtract 1 and divide by 4, you get 1/4. Now, what this is telling us is that if you take 1/3 and you plug it back up in here for t, you're going to get a true statement. It does not tell you that you're going to get 0 equals 0. That's not what that says. It just says that you will get a true statement. Now, if you were to take 1/3 and plug it in here to this step, then you would get 0, right? Because now we're leveraging the idea that the x-intercept, or in this case the t-intercept, whatever you want to call that, is 0 when you plug in 1/3, and the same goes for the negative 1/4. Okay, now that is a very quick example in solving a quadratic by factoring. And again, that's assuming that you remember how to factor. Again, if you're having trouble factoring, then let me know. And like I said, we can talk about that on Tuesday as well, because factoring is going to be important for us. Here is that idea of checking them. Notice again that we don't get 0, but we get a true statement. Again, this is plugging it into the original equation. You could also plug it into the equation when it was solved for t, and you would end up getting a true statement, but it would just happen in that case to also be 0. So this is just checking that. You can look through those. Now, this is what I was saying as the equation may not always start as set equal to 0, but essentially what you end up doing is finding x-intercepts for a function, a quadratic function, but when you're referring back to the original equation, it's not necessarily an x-intercept. So if you look at this equation here, x times x minus 2 equals 3, that is a quadratic. It doesn't look like it necessarily now, but if you multiply it back out, you end up getting this down here, x squared minus 2x equals 3. So it is a quadratic. Now, what we really want to find out is the answer to this. When is it, for what value of x do you get 3 if you plug it in for x and you take x and multiply it by x minus 2? What value or values does that happen? Again, we leverage the idea that it is a quadratic, and then we set it equal to 0 because we end up solving it using the factoring, the 0 product rule. And we find that the solutions are -1 and 3. Now again, for getting everything else on the screen, if you just look at this here, the x squared minus 2x minus 3, then the x-intercepts to that quadratic are -1 and 3. So again, I'll show you that. Let's see. So I'll just show you that. If I can get it. Sorry, I forgot what the function was. Oops. 2x minus 3. Okay, so when we just look at this, and again, this is the quadratic function. Oops, what is that? Okay, this is the quadratic function when that equation is set equal to 0. And notice that when we cross the x-axis, we do cross it at -1, and if I can get it to work, I'll just go over here, and at 3. So it is the x-intercepts for this function. But again, if you go back to the original equation, right, that's not what you started with. You started with x times x minus 2 equals 3, which if you graph the left side as its own function, which is kind of what we did with the linear stuff in the calculator, and you graph the right side as its own function, then the solutions to that equation will be the same as the x-intercepts to this function here. So I'll show you that. X minus 2 and 3. Okay. So I'm going to take this one off for right now. We'll look at it in just a second. And when I plug in 3, notice where these things cross. Again, I'm just looking at the x coordinates here. They cross at -1, and they also cross at 3. Now, if I turn this one back on, which is what that equation ends up looking like as a quadratic set equal to 0, you'll notice that the x-intercepts of this function that I'm about to turn on are also going to be at -1 and at 3. And again, notice that we cross the x-axis here at -1 and at 3. And again, notice those line up with this point and this point. Again, I'm looking at the x coordinates only at the x coordinates. So again, sometimes this kind of gets lost in terms of what we're doing, like why are we looking for x-intercepts if we just started with an equation? And again, I'm just showing you the relationship between the equation that we start with and then how we view it in terms of a quadratic and why we end up talking about x-intercepts. So again, you're more interested in I mean, the whole crux of this is solving this equation. I'm just showing you that we're leveraging that it ends up being a quadratic, and then we can view it as the x-intercepts of the quadratic. So that's, again, that was one using the square root property, using factoring, and now I'm going to show you one using the square root property. Now again, this one's only going to work out in certain cases for us because we're not going to talk about completing the square. But if you have a quadratic and there is no bx term, meaning that you don't see an x by itself, not x squared, not just a constant. I'm talking about if you just see like 5x or negative 12x or 1/3 x, then you're going to end up being able to use the square root property in order to solve it. Now, it doesn't mean that you can't factor. There are certain cases where you can use the square root property and factoring to solve the same quadratic. Again, I told you, you're going to start to see that some methods work out are more suitable for certain quadratics than other ones. So again, I'm just giving you additional tools here. I'm never going to say solve it using this specific way. Now, if you have it set up to where you can get the x squared, and it does need to be x squared by itself, equal to a number, then you can just take the square root of both sides. Now, the square root property says this, that if you take the square root of an equation, meaning you take the square root of both sides, then you have to allow for both positive and negative solutions, because, let me quickly explain why that's the case. For example, if I had something like x squared, and I can't, if I had something like x squared, if I can get it to work, equals 4, then I can't just say that x is 2. That's not necessarily the case, because 2 squared is 4. However, so is negative 2. And if you take negative 2 squared, right, inside the parentheses, negative 2 all squared, then you also get 4. So you have to allow for the negative version of that number to be squared and end up getting 4, which is why you're seeing the plus and minus here. So if I was to solve this using this property, I would take the square root of the left-hand side and take the square root of the right-hand side and put the plus or minus in front of it. And then the square root of 4 is 2, but with the plus or minus, there's the positive 2 version and the negative 2 version. So that's what the square root property is. So here's an example of kind of a small application. Again, remember, anytime anything's dropped or fallen or shot or kicked or whatever, it's going to follow the path of a quadratic. And here's a scenario where you end up getting a quadratic equation. And again, we can talk more about how we got these different values later, but right now I just want to kind of focus in on the quadratic equation. Now notice that it's already solved for 0. That's great. So if you want to use the factoring way of solving, you could do that. You could actually also use the quadratic formula to solve this as well. However, notice that there is no b, in this case t, there is no bx term or bt term. It's only have the squared term and then just other constants or numbers. I don't have just a t anywhere. And so I'm going to end up being able to use the square root property. Now again, you've got to isolate the t squared first. So in order to do that, we perform some algebra. So we subtract, well, in this case we added 16t squared to each side. Divide both sides by 16. Now at this point, notice that the t squared is isolated. So we can take the square root of both sides, but we also have to put the plus or minus in front of it. And then we get two solutions, plus 10/4 and negative 10/4. And once again, let's think about this in terms of graphing. Turn all these off. And I hope I'm able, yeah, we will be able to see this. So we got 100 minus 16x squared. You can use t, it doesn't matter. And again, notice now our a is negative, so this thing is opening down, right? You can see that if we zoom out a little bit. But if we zoom in, we really only care about where this thing ends up being 0. Because that was what the question had asked. I guess that may be relevant here. If you look here, it says, determine how long it takes to hit the ground. Oops, I didn't mean to move that. How long it takes to hit the ground, where h is the height. So, right, we care about when it hits the ground, which is 0 feet. So that's where the 0 came from in this specific example. And again, notice it hits the ground at negative 2.5 seconds and at 2.5 seconds. Now, in the quadratic itself doesn't know that there's a real life context attached here. So it's just going to say, look, this quadratic has x-intercepts or has y values at negative 2.5 and 2.5. In the context of this problem, you can't have negative time, right? Somehow you'd be going back in time or something. That doesn't make sense. So we would actually end up ignoring the negative value in this case and just using the positive one, 10/4, which if you use your calculator, you get 2.5 seconds. So again, first thing to notice is that we're just using the square root property to solve this. And then second is understanding the solutions in context. All right, so that's the square root property. The quadratic formula is the last way that you'll be asked to solve quadratics. Again, when you're using the quadratic formula, you will need to get the quadratic set equal to 0. And that's just so to make sure we have the A, B's, and C's in the correct form, meaning that the signs are correct in the way that we need them in order to plug them into the formula, because this formula is set up assuming that the quadratic is set equal to 0, and so that takes care of the signs of the A, B's, and C's. So from here, if it's in this form here, the standard form of the quadratic, we can plug it straight into the quadratic formula. Now, this thing's kind of ugly. It's not that overbearing, but there is a lot of places that are easy to make arithmetic errors, so just be careful. And but the pro of this is that this will work every time. So the factoring way of solving quadratics doesn't always work. It only works when the quadratic can be factored. And the square root property only works when the quadratic doesn't have that bx term. It doesn't have this linear term, meaning just x to the first, or in the previous example, t to the first. All right, so here's an example of taking a quadratic and plugging it in. So I'm not going to go talk about each thing being plugged in, but you can see the coefficients being pulled out, and then you can see them being plugged in, and then there's some simplification that happens. So the opposite of negative 6 is 6. Negative 6 squared is 36. And then 4 times 3 times 2 is 24. So 36 minus 24 ends up being 12. And then from there, you end up doing some simplification. Now, the way this simplifies is because of what comes out of the square root of 12 and how they simplified this division here. So if you take 6 and divide it by 6, you get 1. That's where this 1 came from. And there's a 1 right in front of the square root, so that's where this 1/6 came from. Also, all that happened was that the 6 was divided into each term. Now from here, this got simplified because the square root of 12, right, is divisible by 4, right? 12 is divisible by 4. The square root of 4 is 2, and that leaves the 3 left over. The 2 comes out, and 1/6 times 2 leaves you 1/3. I know that's really hard to follow with me just saying it. So we can walk through how this got simplified a little further if you want to. But again, think about how we talked about simplifying square roots. You can prime factorize the 12, so it's 2 times 6, and then the 6 is 2 times 3. Or you can think of that 12 is divisible by the perfect square of 4, and the square root of 4 is 2. So again, I know that just we've talked about this. Talking doesn't really help, but we can go in depth in that simplification if you want to go further. Okay, so that's using the quadratic formula. Once again, if you graph it though, so let's see, 3, negative 6, and 2. So if you graph it, again, notice that I've got it looking at 0. So if I graph it, I'm at whatever 4.2 or 0.423 and 1.577. Which should come out to what 1 plus 1/3 times the square root of 3. That should be the bigger number, whatever the 1 point decimal was. And 1 minus 1/3 times the square root of 3 should give you these decimals here. So 0.423 and 1.577. Again, be prepared to give those in both forms, meaning the approximate answer would be these decimals, and the exact answer would be this one. Now, MATLAB is not going to usually let you use the plus or minus. It's going to ask you to separate them in commas. So it would be 1 minus 1/3 times the square root of 3. that's one of the solutions, comma, 1 plus 1/3 times the square root of 3. So you would have two separate solutions there, right? Because it has two different numbers that satisfy it. Okay, again, that's a very quick example of using the quadratic formula. Again, we can talk more about that, but there's your one example all the way through. The last thing, the last big thing is discriminants. The discriminant is just the part of the quadratic formula that's under the radical. So I'm going to go back 2 slides. If you look at the piece that's under the square root, the b squared minus 4ac, that is what we call the discriminant. Now, the discriminant will tell you how many solutions that you're going to end up having. Now, this may seem intuitive once you kind of wrap your head around what that is going to end up looking like or what that's going to end up being. But for now, if you're just taking this at face value, if the discriminant is positive, that means you're going to end up having 2 real solutions, just like we did in this case. So if you look, the discriminant in this case was 12 because it's the piece under the radical, and that's positive, so I end up getting 2 solutions just like we did here. If the discriminant is negative, you end up having no solutions. So again, the part of the quadratic formula that's under the radical is called the discriminant. If you get a negative number under that radical, we don't have a way in our class to handle the square root of negative numbers. So that's why we just say there's no real solutions. And if the square root, if the discriminant is 0, then you end up having 1 solution. Because the square root of 0 is 0. Again, let me show you how this plays out in something that we've already looked at. This is what I was referencing earlier, the 0, the 1, and the 2 solutions cases. So in this case, notice that you have no solutions. That tells us that the discriminant is negative. The discriminant is negative. This has 1 solution that tells us that the discriminant is 0, and you can calculate the discriminant of each one of these, right? You have the A, B's, and C's that you can look at. And in this case, the discriminant is positive because we have 2 solutions. So we've seen that prior. That's what I mentioned earlier, that we may end up coming back to that slide. So in terms of the discriminant, know what it is and then know what it tells you. Here's just a real quick example of looking at a quadratic and then pulling the discriminant out and then explaining what that is. So we have the values of A, B, and C. We plug into the discriminant. We get 0. Since the discriminant is 0, we end up with only 1 solution. So obviously that's a really quick example, but at least you can kind of see it worked out. Here is the using the quadratic formula of that same example. So again, the A, B's, and C's are just coming from this one. You already have the discriminant here. So notice in here we went straight to having 0 here. So the square root of 0 is 0, which adding or subtracting 0 just goes away. And that just leaves you negative 12 over 8, which reduces to 3/2. So again, if you want to see that graphically, so let's see, 4, negative 12, 9. Right, notice that we end up only touching the x-axis in one place at 1.5, which is 3/2, right? 3/2 is 1.5. Okay, so I'm going to basically stop there. There are some applications of quadratics and using the solutions to quadratic equations to infer things. So there's like all kinds of ways that we can use these things. So they have applications in geometry and then in physics, and there's a lot of places. So I just have one example of this kind of worked all the way out. Guys, you will have some smaller things to work on your exam in terms of things to solve and setting up equations and things like that and being able to solve them. So just know that's coming. Okay, guys, I'm going to stop it here because this video is already kind of long. Again, if you have questions or anything, please let me know. You're more than welcome to email me before the end of, or before class on Tuesday. But this is something to get us started with 3.1 and 3.2, and we can obviously talk more about anything that's in here, but I wanted us to have a good jump start for Tuesday when we come back. Again, I look forward to hearing from you, and if I don't hear from you between now and class, I'll see you in class on Tuesday, which I believe is, what is that? February 27th. Okay, guys, I look forward to hearing from you.